Okay, let's continue. And just now I asked you guys to add two more KNN models into the ensemble. And by my observation, this dataset is not beautiful, but it's not really bad either. So, in most of the cases, and if you try a small k number, that should be okay, except for the overlapping part. So in this overlapping part, I definitely want to try to use a excuse me, a k value higher than 1, but I don't think I want to try a larger value. So instead, I decided I want to try the k value to be 5 and 7. Okay, so I added two more KNN classifiers, and then I gave them the two names KN5 and the KN7. So in this case, I retrained the ensemble, and then I try to get the performances of the KN models and plus the new voting classifier. So, I got the 90.4%, so which is, actually exactly the same as I got before. So, adding two KNN model didn't really bring us too much improvement. Okay, so what's a potential problem with the two KNN models we just added? Okay, so I already showed you the answer key. So the one of the problem is the scaling. So remember, why do we want to do scaling? We only need to scale the dataset if we are measuring the distances between the samples. Remember that. So for the decision tree, do we want to do scaling? The answer is no, because in the decision tree we are not making any decision on based on the distances between two samples, right? We don't do that. So in this case, if you're doing the decision tree, you don't need to worry about the scaling. However, if you're adding the KN models, we do have to pay attention to the scaling. So we didn't do scaling. Probably that's the reason that the KN models didn't perform very well. And if we do the scaling, I suspect the KN models might be a little bit better. And the number two, which is the even bigger thing, that is those two KN models, they are not independent. Why? Because they are both KNN models. Okay, so imagine that if we add 1 year's neighbor, 3 years neighbor, 5 years neighbor, 7 years neighbor, and 9 years neighbor. So we add 5 nearest neighbor algorithms into this ensemble, and what is going to happen? So for those KN models, well, the working mechanism are the same. So they are not that independent to each other. And in a lot of the cases, you may find that they vote for the same class every time. And then this is collusion, right? So you have the KNN models and then they always collude and then make the same prediction. We don't want that. And this brings us to the next point, which is, ensemble method works the best when all the predictors are independent. The voting is only meaningful when the voters are independent. If they collude and then they can damage our voting system, and we don't want that. So the next question is, if we want all the predictors to be independent, how can we do that? And the easiest thing is, for each of the machine learning model we know, we create a predictor. So for example, like the first ensemble we created, that is a logistic regression, a decision tree, and the SVM, they are all different machine learning models. So they are not colluding because they are quite different models, right? Okay, so this is the first idea. But what's the problem? The problem is, there are only a few dozens of the predictors built in scikit-learn that we can use. So this means the largest ensemble we can possibly do if we want to have different type of the machine learning models should be roughly a few dozens. That's the largest ensemble we can possibly do to make all the machine learning models independent if we are trying to use different machine learning models. So I think that works. But if we want to have more voters, more predictors in the ensemble, how can we do that? So here is another idea. So how about we just stay with the same machine learning model? However, for each of the machine learning model, we feed a different dataset. So let me say it again. Well, we are creating a bunch of decision trees. However, if we want to make all the decision trees independent, one thing we can do is we train each decision tree with a different training set. Okay? So in this case, this will make all the decision trees independent to each other too. Okay, so the next part is how do we create the independent training sets for each of the machine learning model. Okay, and then there are two ways. Well, one is called bagging. So if we want to sample the training sets with replacement, and then we call that bagging. And otherwise, if we want to sample the samples without replacement, and then that is called pasting. Okay. So, and the next question is for the bagging and pasting, what are the difference? So for the pasting, well, what is pasting? Pasting is without replacement, right? So for the placement, well, it is designed for the larger set and limited computational power. Okay, so if you're doing pacing, the scenario is more likely to be you have a really huge data set and you don't really want to use all the data set for training purpose because the data set is too large. Well, you can use the full thing, but the machine learning model will be slow, and well, you ain't gonna gain anything by making use of the full data set. Probably only 10% or even 1% of the data should already be enough. So that is the pacing. And for the bagging is better for the smaller set because when we are sampling the the training set, and then we are doing that with replacement. So if we draw one sample from the training set and then we draw that again, it is possible that we draw the same sample again, and actually we want that. The reason is, well, if you're doing the bagging, usually we have a limited size of the data, and that may not be enough. So we just use the bagging to slightly increase the size, the data set a little bit. So that is the bagging. Okay, so after knowing the pacing and the bagging, the next topic will be how about we have a bagging classifier. So for the bagging classifier, we are still trying to build an ensemble. However, in this ensemble, we are going to create a lot of the machine learning models of the same type. So let's take a look on this one. So this is the bagging classifier, and then we are creating decision trees. We are only creating decision trees, and then see the n estimators, that is 500. So we are creating a total of 500 decision trees. And then the max sample size, that is when we are drawing from the training set, we are trying to get the max of 100 samples for each of the decision tree. And then the bootstrap equals true, that is the drawing samples with replacement, and the n drops, that specifies how many processors or the cores you're going to use, and finally the random state. Okay, so we train the bagging classifier and then we make the prediction. So we got a performance of 90.4. And what is that? That is the performance of an ensemble of a total of 500 decision trees. Okay? So if we want to just build one single tree, so if we build one single tree and then we train that and then we get the performance, and then you got a 85.6%. So this means if we are having an ensemble of 500 trees, this will be better than having only one tree. Okay, so this video is already long enough, and I will see you in the next video.